Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashidu Mamboro. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Welcome to this lesson. We are continuing with organic molecules. We'll be focusing on a little bit of naming and physical properties. The main topic that we'll be dealing with today is physical properties. So I'm hoping that you are ready. You have your pen and paper. You are going to be part of this lesson and you are going to gain a lot. So ensure that you listen, you take some notes. There will be some questions. If I give you questions, answer them and be able to answer those questions. Remember, it's still part of paper 2, as indicated that here we're talking about 38% of the paper. We are saying that is chemistry is 20 multiple choice questions. We always remind you that 130 marks will come from structured questions. And we are saying to you plus or minus 58 marks will come from this organic molecule. So it's important that you have a good foundation and you have a good understanding of the topic. And then you check last year, question 2, which is naming of organic molecules, nomenclature, organic structures. This one, the learners were performing at 65%. But if we look at question 3, which is physical properties, the one that we're going to do today is 60%. We can perform better. It can be 100% there. Then we know that we are doing well. Then question 4, still on organic molecules, learners will perform at 49%. So you can see the graph, how it's going. We are trying to make sure that we perform even much better than this, so that at least 80-90% there in terms of learner performance in terms of this topic. Now, without any wasting of time, we'll go to our subject framework. We are dealing with this one now, which is our week 7. We're having physical properties there. So that's what we'll be dealing with today. And then we are saying activity 1. Now, it's important, remember, you have done naming of organic molecules. So now here we're going to focus on drawing of structural formula so that you know how to draw the structures and you are able to collect marks. I think you have seen most of question papers, you'll find questions like this one. So it's important that you know how to draw the structures. So there are two things. You can be given structures and asked to name them using IUPAC naming, or you can be given IUPAC name and then you are asked to draw the structures, as we have here in this activity 1, where we are expected to draw the structures. Now, the main thing, remember we said the name has 3 parts that we focus on. We said we focus on the suffix, which is how the name ends, and this is coming from functional group. Remember, functional groups tells us about the homologous series. So this is the suffix. We'll look at the functional group, which will tell us which homologous series the compound belong. And then after that, we're going to look at number 2, which is now the second part, which is the root or the parent, the longest carbon chain. We're going to look for the longest carbon chain. Remember, we said when you have 1 carbon, we said it's meth, 2 carbon is eth, 3 carbon is prop, 4 carbons is put, 5 carbons is pent, 6 carbons is hex, 7 carbon is hept, 8 carbon is opt. Remember, in physical science grade 12, we do up to 8 carbons. So you have to know in the longest carbon chain, how many carbons do we have? And you will number them like that as we indicated. Now, without wasting of time, we said suffix from the functional group. Now, number 2, we're saying the parent chain, and the parent, we're saying we get the parent from the number of carbons, the longest carbon chain. How many carbons do we have? I've already indicated that is how we get a parent. And then the third part of the name will be the prefix. The prefix, and for the prefix here, we're saying these are substituents. For our topic, it has been made much easier for us. Remember, our suffix is our prefix is our halogens. We're talking about your chloro, your bromo. We're talking about your iodo and your fluoro, if they're included, but mostly bromo and chloro. And we're talking about your methyl, we're talking about your ethyl. Those are our prefix. We call them substituents. So those are our substituents that we are expected to have. So when you see them in the name, you know they are not part of the longest carbon chain. They are just branches if they are alkyl groups, or they are just substituents if it's your bromo, your fluoro, your iodo, and your chloro. So I think you got that, and we're going to draw the structures looking and following the same method, because this is going to make it much easier for us. Now, without wasting time, you see that this is an alkane, because you can see the ane there is showing you that the homologous series there is alkane. So you know that you are dealing with an alkane, which means alkane, we know they are saturated. They are saturated, they have no multiple bonds between carbon atoms. Remember, that's how you define saturated. Now, we are saying is ane, so you know that. You check now, the parent is hex, which means 6. So you have 6 carbons that are saturated, that doesn't have a multiple bonds between them. So the first thing that you will do, you will draw your 6 carbons. Remember, we said carbon always must have 4 bonds around it. Those are the most important things that you must have. That is your hex now. You see that your hexane is like that. And then we are saying in carbon number 2 and carbon number 3, we have a dichloro. And in carbon number 3 again, we have a methyl. So that is very much important. You see, in terms of the homologous series, we said this is an ane. The name will end, it ends with an ane. In terms of the parent, we said it's hex, which means 6 carbons. In terms of the prefix, we are saying we're having 2,3 dichloro. So in carbon number 2 and carbon number 3, we're going to have chloro there. Chloro in carbon number 2, another chloro in carbon number 3. Hence, we're saying 2,3 dichloro. So you're able to put carbon number 2, you put a chloro, carbon number 3, you put another chloro. So that is 2,3. And then in carbon number 3, you have a methyl, which means you have a CH3 there. Remember, they said structural formula. You can't write CH3 like CH3. You will write it as carbon bonded to 3 hydrogens. So please, when it's a structural formula, we said we show all the bonds. So you are able to see that this is 2,3 dichloro, 3 methyl. Then remember, all the carbons must be having the hydrogens now that remains. We put the hydrogens there. Then you are able to see this is how to draw 2,3. So this one is like a direction where it's telling you where are your visitors. We are saying in carbon number 2, we have a chloro. In carbon number 3, we have another chloro. Hence, we are saying 2,3 dichloro. In carbon number 3 again, we have a methyl, and we have indicated that. I think you have understood, and you can see how easy it is to draw this structural formula. They can ask you from here, draw molecular formula. You are able to draw it. Write down the general formula. You will see these are haloalkanes. So these are haloalkanes. That's that we have a substituent there. Now, question 1,2, it says 2 methyl but 1 ene. Again, what is happening? We always starting there. The ene there, you know, it stands for the double bond. So you know that we are going to have a double bond in carbon number 1. So already you're given the position there to say in carbon number 1, we have a double bond. And how many carbons do we have? We have 4, because it's put is 4. So all you're going to do, you're going to throw your 4 carbons. And in carbon number 1, you're putting a double bond. I'm intentionally putting the double bond on the right so that you are aware that carbon number 1, it can be on the left or on the right. Doesn't mean that always you're counting from the left to the right. You can count from the right to the left. So this is carbon number 1 in this case. So we are saying this is put 1 in. Remember, your carbon at all times must have 4 bonds. Always count them. Always ensure that around each carbon you have 4 bonds. I think you saw how to draw that. That will be put 1 in. But I've drawn put 1 in. I didn't draw 2 methyl. So they're saying in carbon number 2, we have a methyl. We don't have a hydrogen, because if you draw like that, you are going now to have been, you have drawn put 1 in. But they're saying in carbon number 2, we have a visitor there who's replacing a hydrogen, which is a 2 methyl. So you must know that you have a methyl there, which is a CH3. Methyl is a CH3, so you are able to put a CH3 in carbon number 2. Then that is your structure for 2 methyl, put 1 in. I think you can see how simple to draw the structures. And throughout your paper, can go to previous question papers. You will see questions like this. You will definitely be getting them. So go and practice as many as you can. Start from the suffix to the parent to the prefix. As I'm doing here, you can see we're given 3 methyl pentanal. So you see that we have at the end al there, al for aldehydes, al for aldehydes. So you know al, that al is a C double bond O and an H. Remember, with aldehyde, the C double bond O is in carbon number 1. With the ketones, the C double bond O is surrounded by 2 carbons. But this one, because it's an aldehyde, you will definitely have carbon number 1 as a C double bond O bonded to the H. Remember, a carbon must always have 4 bonds. I'm always emphasizing that. Then you see that that is the al that we have drawn. That is the functional group of aldehydes. And then they are saying it's a pentan. Pentan means 5 carbons. 5 carbons. So we have 5 carbons. This is 1, 2, 3, 4, 5. That is your pent. So you see that the pent, you have met the pent, you have met as well the al there, so it's pentanal. Now, what is left is that we have a visitor in carbon number 3, 3-methyl. We're having in carbon number 3 we have a methyl. So you just go, carbon number 1 is always the one that is having a functional group in terms of aldehydes. For aldehyde, carbon number 1 always has a functional group. Remember, a functional group will always get a priority in terms of numbering. You will always number closest to the functional group. So because this is the functional group, so you know that this is carbon number 1. Number 2, we're looking for carbon number 3, which is this one. And there we must put a methyl here, which is a CH3, and then you just put a CH3 there, and then that is your 3-methyl. Then don't forget the hydrogens. Immediately we find 1 carbon without hydrogens, without 4 bonds around it, the answer becomes wrong. So be careful that all the time you are checking that all your carbons have 4 bonds around it and there are hydrogens around them, except where we're having the functional group or the substituent. So in this case, that is 3-methyl pentanal. 3-methyl pentanal. You see, you must indicate all the hydrogens. Oh, sorry, you must indicate all the hydrogens. It's fine. The carbon must have 4 bonds so that we don't make a mistake there. So always check the number of bonds around a carbon. So we are moving now to the last question, which is 1.4. It's saying this one is 3,4. 3,4. Remember, you said you put a comma when you have like terms. So like you're having a methyl and another methyl. So you're having 2 numbers. Between the 2 numbers, you put a comma. But between unlike terms, like a number and a letter, you'll put a hyphen there. Hence, we are saying 3,4 dimethyl pentan 3-ol. We start with a functional group, which is the ol, which is the OH. Now we're having OH in carbon number 3, and that is the functional group. So we know that the functional group is the OH and it's in carbon number 3, and the name is pentan. You know pentan is 5 carbons. So we are going to draw 5 carbons. 1, 2, 3, 4, 5. You have your 5 carbons there. In carbon number 3, you're going to put your OH there because that is your 3-ol. Then you ensure that all the other carbons are surrounded with their hydrogens, and they must be not less than 4 bonds. They must not be more than 4 bonds. So the number of bonds around the carbon, they will at all given time be 4 bonds around the carbon. So you draw it like that, and that is your that is your pentan 3-ol. You see that. Then don't forget, in carbon number 3 and carbon number 4, we have a dimethyl. Always don't forget the substituent there. That we have a visitor in carbon number 3. So that is the same carbon that where we have an OH. Carbon number 3, we have a methyl, which is a CH3 there. Which is a CH3 there. In carbon number 4, we have another methyl. Please don't make a mistake of leaving them out because the whole structure becomes wrong. Please ensure that you have indicated all the structure. So when you are done, go back to the name again and say in carbon number 3, do I have a methyl? Yes. In carbon number 4, another methyl? Yes. And then do I have 5 carbons in the longest carbon chain? 1, 2, 3, 4, 5. Correct. Do I have OH in carbon number 3? Yes, OH in carbon number 3. And you show all the bonds because these are structural formula. I think you have learned and you have understood how to draw structural formulas. And as and when you are asked to draw any structural formulas, you will be able to draw. And you will see that this method of dividing it into 3, it makes it much easier. And when we mark, you will find that we're going to give you a mark for writing hexane there. Correct parent, 6 carbons. We're going to give you a mark for identifying the substituents correctly. That is mark number 2. We're going to give you another mark for the correct numbering. So it's important that you know that this question can be worth 3 marks. and you can always collect those marks. So please practice as many problems as possible, and you will be able to see that there is nothing here. This is not difficult. Now, the issue of the isomers that we're supposed to talk to them to say we have structural isomers. In terms of structural isomers, we're saying these are organic molecules with the same molecular formula but different structural formula. So they have different structural formula, but molecular formula is the same. Now, we're given here chain isomers. You're able to see that we're given there a butane, and each isomer has a branch. So when you have a branch, you know that those are isomers, provided the molecular formula is the same. Same molecular formula, but different types of chain in terms of this, because this is unbranched, this is branched, so it's different types of chain. This chain and this chain are different, hence we are saying chain isomers, they have the same molecular formula, which is correct here, but different types of chains. I hope you got that. And the one thing that I want you to understand is that both butane and 2-methyl propane, they belong to the same homologous series. They are all alkanes, hence we are saying the name, it ends with ane. They are all alkanes. So chain isomers are within a homologous series. So when you talk about chain isomers, you cannot have an alcohol and a carboxylic acid and you say they are chain isomers. They cannot be. Why? Because chain isomers are within a homologous series. They must belong to the same homologous series. That's what we are saying, the first thing. The second thing, we're saying they must have the same molecular formula. The third thing we're saying now, they must have different structural formula, which means that they must have a different number of branches, which means we are saying this one 0 branch, this one 1 branch. So you are able to see that as I look there, these are same molecular formula but different types of chain. I think I've explained it nicely and you have understanding, and it will help you as we move forward. Now, positional isomers. We are saying for positional isomers, we're saying these ones now have the same molecular formula. So all isomers, they have the same molecular formula. They are organic molecules with the same molecular formula. That one you must always know. Iso means same. Iso means same. So you know that, oh, same what? Molecular formula. But what is different? You look at the name. The name will tell you what is different. Same molecular formula, but different position, because these are called positional isomer. Different position of what? Of the side chain, of the substituent, or functional group. Please, learners, don't forget that what is different on positional isomers is 3. I call it SSF. Don't write SSF in the exam, because we had situations when learners are given mnemonics or things that will make them to remember. They now go and write that in the exam. When I say different SSF, I'm just making it easier for you to remember, but you can't write that in the exam. You must know that what is different there is the side chain, is the substituent, is the functional group on the parent chain. Now, as well, positional isomers like chain isomers, they happen within a homologous series, within one family. Remember, we said we have 9 families in these organic molecules that we do in grade 12. So within a family, you will find chain isomers. Within a family, you will find positional isomers. And we are saying now, these positional isomers, they will have the same molecular formula. Look at that, C4H9Cl. Even when you count here, you will find 4 carbons, 9 hydrogens, and 1 chlorine in both structures. But what is different will be the position. In this case, is the position of the substituent. Remember, we said chlorine is a substituent. So our substituent is in carbon number 1 here. Our substituent is in carbon number 2. Hence, when we name this one, you will call it 1-chloroputane, and this one you will call 2-chloroputane. So the name of isomers won't be the same. When you name isomers, you will see that the name is different. The name must be different. But what is the same will be the molecular formula. But what is different will be the position. Immediately when you change the position, you are changing the name of the organic molecule. So I'm still saying positional isomers are within a homologous series, and I'm saying they all have the same molecular formula, but different position of the functional group, of the side chain, or the functional group there, the side chain, the substituent, or the parent chain. Now we are saying different position of the functional group. For example, it will be OH, carbon bonded to OH. That is a functional group. So when a carbon is bonded to OH, remember, learners, we want to always emphasize the issue of the functional group. To say OH on its own is not a functional group, but OH bonded to a carbon, it's a functional group. So the functional group is that one. So you're able to see that when we change the position of the functional group within a structure, we're going to get positional isomers. But now, when it comes to a substituent like chlorine, when you change its position, you will get again positional isomers. So positional isomers are about that. We can move around the functional group. We can move around the substituent. All those situations will give us positional isomers. I hope you got them and you understand them. Now, my favorite of functional of the isomers is these ones that are called functional isomers. We give it a name to say this for you to remember. Just remember the cake. I think you like the cakes during your birthdays. Now we're saying a cake because we're saying carboxylic acids and esters are functional isomers. Aldehydes and ketones are functional isomers. So you know that when you say cake, you have it in mind, just to make you remember at all the time, because we want you to enjoy your lessons as you are studying, to say, I know this one, the cake, it stands for carboxylic acid and esters. Remember, when we were doing general formulas, we said the general formula for carboxylic acid is CnH2nO2. For esters is CnH2nO2. So you can see that carboxylic acid and esters, they have the same general formula. And then when it comes now to the molecular formula, it will be the same situation there. You can see here we're given an example of methyl methanoate, which is now 2 carbon C2H4O2. We're given here ethanoic acid, which is C2H4O2. You are able to see there that all the molecular formula is the same. Just write the molecular formula. Remember, to get a molecular formula, we are simply saying count how many carbons we have. 2, correct. How many hydrogens? 4. How many oxygens? 2. You write it like that. Then you do the one for carboxylic acid. You will find that for when an ester and a carboxylic acid have the same molecular formula, but they belong to the different functional group. Hence, we are saying have the same molecular formula but different functional group, and those are called functional isomers. This is the only type of isomers where they don't belong to the same family. They don't belong to the same homologous series. Remember, esters, carboxylic acid, aldehydes and ketones, they don't have the same, they don't belong to the same functional homologous series. Now CnH2nO and is for both aldehydes and ketones. So you see that they have the same general formula. So if they have the same number of carbons, it means now they will have the same molecular formula. And if they have the same molecular formula, we are saying what will be different will be the position. Remember, for aldehydes we said it's C double bond H in carbon number 1. For ketones we said it's a C double bond O surrounded by 2 carbons around it. So you are able to see at all given time that, okay, the difference between this and this is that the C double bond O is in carbon number 1, the C double bond O is surrounded by 2 other carbons. So this functional group is important that you always remember them. And then we are saying these are functional isomers, same molecular formula but different functional group. Hence we said the cake, carboxylic acid and esters, aldehydes and ketones. I hope you got that, and you'll be able to remember that even as and when you write your exams. Now, without wasting time, we're able to move as well, so that we move to the next question, and then we're able to deal with it. It's just what I was explaining in terms of aldehydes. You can see we're having butanol there, and we're having butan 2O. They will have the same molecular formula, but different functional groups. So you see that the cake, it works for us in terms of that. But as it comes to chain isomers, we said the same homologous series. Positional isomers, same homologous series, different position of the substituent, of the side chain, and the functional group. Positional isomers, we talked about that to say we are changing the position of the functional group or the position of the substituent. But when it comes to functional isomers, then these ones, they have the same molecular formula, but they have different functional groups. I hope you got that, and you'll be able to answer to questions that have to do with that one. Then when those questions comes, you are able to respond to them with no any problem. Then you are able to see that you are doing well. Now, I will say, as we move to our alcohols, it's important that you understand the types of these alcohols. We do primary alcohols, secondary alcohols, and tertiary alcohols. And we are saying all these primary alcohols, we don't only do primary alcohols, we do primary alcohols and primary haloalkane. So you got to know that the same will apply to a haloalkane, the same will apply to an alcohol. Now, when it comes to an alcohol, primary alcohol, we're saying that the carbon atom that is bonded to the hydroxyl group is bonded to one other carbon. We're saying the carbon that is bonded to the hydroxyl group is bonded to one other carbon. You can see the first carbon there is bonded to the OH. We're saying that carbon, how many other carbons is it bonded to? So you see that it's bonded to one other carbon. And then when it comes to haloalkanes, the same thing. The carbon that is bonded to the halogen is bonded to one other carbon. So that is your understanding. You only focus on the carbon that is bonded to the halogen for haloalkanes. You're saying this carbon that is bonded to the halogen, how many other carbons is it bonded to? So if the carbon that is bonded to the halogen is bonded to one other carbon, we call it a primary haloalkane. And if it's alcohols, we are saying when the hydroxyl group, the OH, when the hydroxyl group is bonded to the carbon that is bonded to the hydroxyl group is bonded to how many other carbon? When it bonded to one other carbon, we call it primary. I think already you understand secondary now. That okay, the primary one, the carbon bonded to the hydroxyl group is bonded to one other carbon. For secondary, obviously, it will mean that the carbon that is bonded to the hydroxyl group must be bonded to two other carbons. So we're increasing the number of carbons that are bonded to the carbon that is bonded to the hydroxyl group. The same applies when it comes to secondary alcohols. Now, in terms of secondary alcohol, we still focus on this carbon to say the carbon that is bonded to the hydroxyl group is bonded to two other carbons. Hence, we are calling it secondary. I think you know, you start school at primary. The second school you go to is secondary. From there, you go to tertiary. So you will have an understanding to say when you go to tertiary, we're expecting that the carbon that is bonded to the hydroxyl group will be bonded to three other carbons. So that's how we're moving. Primary, the carbon bonded to the hydroxyl group is bonded to one other carbon. Secondary, the carbon bonded to the hydroxyl group is bonded to two other carbons. Tertiary, the carbon bonded to the hydroxyl group is bonded to three other carbons. I hope you got that. The same applies to haloalkanes. To say in haloalkanes, the carbon that is bonded to the halogen is bonded to two other carbons. We call it secondary alcohol. Now, when you go to tertiary alcohol, we are saying the carbon, forgive me here, there must be a bond because these are structural formulas. And then unless if it's not it's a semi-condensed structural formula like that. But if you are asked to write a structural formula, you will show all the bonds. But here it was just the main thing that we wanted to show is that the carbon that is bonded to the hydroxyl group, that is your focus. You focus to the carbon that is bonded to the hydroxyl group. How many other carbons is it bonded to? And definitely it's bonded to three other carbons. Then you are able to see that this is a tertiary alcohol. The carbon that is bonded to the halogen, how many other carbons is it bonded to? It's bonded to three other carbons. So you are able to see that this is a tertiary haloalkane. So you're able to collect those marks. I hope you have that. It's important, this one, more especially the primary alcohols, because now we're going to use these primary alcohols during esterification. Remember, esterification, we are saying, is when a primary alcohol is treated with a carboxylic acid in the presence of sulfuric acid. So sulfuric acid is a reaction condition. We are saying without this sulfuric acid, this reaction, it won't be able to take place. So it's very much important that we have a primary alcohol we have carboxylic acid, and here we have our catalyst, which is sulfuric acid. Hence, esterification will be able to take place. And they were saying this compound is a sweet smell. The compound is obtained is called an ester. So esterification is a process where an alcohol react with a carboxylic acid to form an ester and water. So we have water is one of the products that is formed. Now, I want you to have an understanding to say an alcohol that we're talking about is an organic molecule. A carboxylic acid is an organic molecule. An ester is an organic molecule. And all of these, we said, they are homologous series. But if you look at water, it's an inorganic molecule. So we call water an inorganic product. It's an inorganic product because I'm emphasizing this because sometimes in the question they will say write down the inorganic product that is formed, and learners they don't have understanding of which one is inorganic, which one is organic. Remember when we started this topic, we said organic molecules are carbon containing compounds. There must be those carbons there, and you can see your water is free of carbons. So you are able to see that this is an inorganic product. Now, that was our word equation to say we're having our methanol plus methanoic acid forming methyl methanoate. We said the reaction condition is H2SO4 sulfuric acid. H2SO4 is sulfuric acid is our reaction condition. It means that for this reaction to take place, there must be that sulfuric acid. Now, what am I saying? We are saying that we're having methanol here plus methanoic acid, they're going to form methyl methanoate. Now, this methyl methanoate is an ester plus water, so there must be water as well. There must be water as well because it's two products that are formed, organic product and an inorganic product. Now, if you look at methanol, the way it is now, you can see that we are going to change the anol from methanol there. It will become YL, the IL, the alkyl. Remember, if you are having CH4, for example, you call it methane. CH4 is methane. But if you are having CH3 running short of one hydrogen, it's no longer methane. Hence, we are saying our substituents, we call them methyl. So it's the same there. So you know that methyl means CH3. Methyl means CH3. So you are able to get that. If you are having, for example, ethane, ethane is CH3, CH3. If you are having CH2, CH3, you know that we are running short of another hydrogen. So that is not longer ethane, is what? Ethyl. So you are able to say how these alkyl groups are formed. Is when we remove one hydrogen from your alkanes, you will get the alkyl groups. So you're able to see them. They are branches. They are branches on the structure or the side chain. We call them side chain branches or substituent. We're using those three words interchangeably. So have an understanding of what is happening. So in this case, if I can use the example of methanol and methanoic acid forming methyl methanoate, which is an ester plus water, is that methanol is your alcohol. So it's a carbon bonded to the OH. That is your methanol. We use primary alcohols here. We have already, that's why we started by telling you what are primary alcohols so that you don't forget. So we're having methanoic acid, but I want to bring, because we want to form water, so I'll bring the functional groups to be next to each other. Remember, for the reaction to take place, the functional group must be able to interact with one another. So you're having methanol there and methanoic acid. I want you to have an understanding so that we move together. So what happens there is that this H from alcohol and this OH from methanoic acid will form water. So that's how water is formed. So I think you are clear about that. Yes, that's how water is formed. I'll just write it here. That's where your water is formed. Now, how the product is formed here is that we are going to write this structure without this water. You just write the same thing. So I'll just copy. The same is bonded to the oxygen, is bonded to the C double bond O, and then H is bonded to CH3, so it's CH3 here. And that is our methyl. This is one is our methyl. And then this one is our methanoate. You can see we were having this oxygen going with this CH3 here. Hence, in our name, we say the methane, this part, has 8 the oxygen from here. Hence, O8. You see the O8. This oxygen now becomes part of this part of the last part of the name, the parent chain. And this one is our alkyl group, which is methyl. So the oxygen now is part of this one. Hence, we are saying it's one carbon, so it's methane. So we're saying it's methane O8. Methane O8, that O. Methane O8. Then you are able to see that we're having a methyl now and a methane O8. So that is the name of the ester. Remember, when you write names of the esters, they have two names. You don't write this as one name. Remember, all the other homologous series, with exception of esters and carboxylic acid, they have one name. Only esters and carboxylic acid you can write methyl methanoate, ethanoic acid with a space in between. But with other names of the 7 homologous series, you write one name at all given times. So have that understanding. So what is left for us is just to increase the number of carbons going that side and going that side. So you can see, if I put another carbon there, it will be ethanol. So it will be ethyl. If I put another carbon this side, it will be ethanoic acid. So the name that will be formed, it will be ethyl, because the alcohol is always becoming the YL, there is always becoming an alkyl group, and the carboxylic acid is always become the O8, the propanoate. Propanoate means now we're dealing with 3 carbons. So as you increase the number of carbons, you're just checking how many carbons. 3 is prop, 4 but, so you'll have butanoate, depending on the carboxylic acid that you have used. So I hope you have this esterification with you, and then you'll be able to answer questions that relate to esterification. So this was just a further explanation for you, so that you have a much better explanation. So you're able to see we're taking the H here from the alcohol, we're taking the OH here from the carboxylic acid, and we are using sulfuric acid there, H2SO4, as our catalyst. And then we're able now to have that, and we're saying because it was ethanol and ethanoic acid, we're going to say ethyl ethanoate, ethyl ethanoate. So you're able to see that this is our ethyl part, and then the ethanoate, the one that eats the O, is this one is the ethane, the 2 carbon. So it's ethane O8. That oxygen is now part of that. I think that will help you to remember. It is just my creativity to say you can remember it like that, to say, okay, we're having an alcohol, we're going to remove only H, and then the other structure will take the oxygen and it will be part of it. Then it leaves the alcohol as an alkyl group instead of having an oxygen as well. So I hope that helps you. And when you say structural formula, this is how you draw structural formulas. You can get this question with 5 marks. So I'm saying here, take this into consideration. We can give you molecular formulas and say do esterification. Don't think that you will always be given alcohols as structural formula. You can be given the same structure as C2H6O. You got to be able to see that that's an alcohol, and then that reacting with the carboxylic acid there, which is now C2H4O2. So you got to be able to know that this is a carboxylic acid. Anyway, you know that we only have 2 homologous series that have 2 oxygens. So this one, it will be easy for you because you want to form an ester. This must be a carboxylic acid, and then this one you must be able to draw it first, so that you are able to see when you draw structural formula, you'll be able to see where the bonds are going. You will be able to get an alcohol, and you know that this is your alcohol. So we're saying no, as you practice these questions, use molecular formulas and use condensed structural formulas as well. Not only structural formula, just that with structural formula is more visible, and it becomes much easier for you to see. So I hope with esterification you are happy, and that's the part that I wanted to to finish that part of the lesson. Now we're going to focus on the second part of our lesson, which is physical properties. I think this is a very nice topic that if you understand it and you have done it well, you will do very well in terms of this topic, which is question 3 of our paper 2. Now, In physical sciences, we do 3 physical properties, which is the melting point, the vapor pressure, and the boiling point. So when you say physical properties, we're talking about those 3. There are 3 physical properties that we focus on in grade 12. As you go to university, you can do others, viscosity and other physical properties. But for grade 12, you are focusing only on melting point, vapor pressure, and boiling point. And there's a reason why I arranged them like that, to say melting point first, vapor pressure, boiling point. Remember, let's take ice from your fridge, from your refrigerator. You are having ice, which is a solid. You increase energy, you heat, you give it heat, you give it energy. When you increase energy, you overcome the intermolecular force. Remember, ice have what you call is water. Ice is H2O. Is that is water in a solid form. So that ice that I'm referring to is the water, the ice or water ice, not the other one ice that you might have. The one that is made up of water. I'm saying if it's in a solid form, when you increase temperature, you overcome the intermolecular force, which is the hydrogen bond that are holding the water together. So we're saying water is held together by hydrogen bonds. So immediately when you increase energy or when you heat it, what is going to happen is that you are going to overcome the intermolecular force. Why not break? We don't break the intermolecular force, we overcome it. So it means when you overcome it, the solid will become liquid. That solid becomes liquid, and that is what we call melting. Melting is when a solid becomes liquid. I want to clarify that. Melting and melting point are 2 different things. Now, I'm still talking about melting, which is when the solid changes phase to liquid. That is melting. But now, this one that I'm talking about here is called melting point. Now, for melting point, we are saying it's a temperature at which the solid phase and the liquid phase are at equilibrium. So you are having an equilibrium there. It means the rate at which the solid is forming the liquid is equal to the rate at which the liquid is forming the solid, which means that at the melting point, you are having both solid and liquid. You don't have only liquid. Hence, you are saying the solid phase and the liquid phase are at equilibrium. So you know, melting point is not a point, it's a temperature at which the solid phase and the liquid phase are at equilibrium. Please have that understanding, to say the first thing I will talk to is the melting point, because it's between the solid and the liquid. And we're saying at the melting point will be the temperature. Like if you are saying the melting point of water is 0 degrees or 4 degrees, whatever the substance that we are talking about, it will have a melting point. So when you're saying the melting point is 0 degrees, for example, then you are saying at that temperature, the solid phase and the liquid phase will be at equilibrium. So remember, melting point, we are saying the solid phase and the liquid phase are at equilibrium, but it's the temperature, it's not a point. So if we say define melting point, and you say it's the point, we're no longer going to continue to read your statement. We'll just give you a 0, because melting point is a temperature at which the solid phase and the liquid phase are at equilibrium. I hope I've emphasized that. You have the understanding of that. Now we move to vapor pressure. So at equilibrium, we're saying the solid phase and the liquid phase are at equilibrium. Now I always ask learners this question, to say what comes first, the boiling of the water or the vaporizing? When the water becomes vapor, which one comes first? And learners, they think that boiling comes first, then vapor after, and it's wrong. Remember, what is happening is that you are having a container, and your container, you are putting it on a source of heat there. It can be a stove or anything, and it's closed, this container. What happens is that in the atmosphere here, we're having above sea level, we're having atmospheric pressure. It's called 101.3 kilopascals. It's our atmospheric pressure. It means the pressure above sea level is 101.3 kilopascals, which we can call it we can call it 1 atm. 1 atmospheric pressure is still another SI unit we use, atmosphere. The atmospheric pressure one is the ATM, 1 atm. So 1 atm is a standard what? Is a standard pressure. 101.3 kilopascal is a standard pressure. And that will apply. Sometimes it will give you the same pressure in millimeter mercury, mmHg. Still, we're referring to that, then it will be 760. So it doesn't matter the SI unit, but for your understanding, we're saying atmospheric pressure is 101.3 kilopascal, and then or 180 m. Now, let's move to the lesson. Now, you're having your substance there, can be water. What happens is that as you heat your water, the water will start to vaporize. There will be vapor that will vapor pressure that will develop within the substance. Which means now these molecules, they will start to collide with one another and with the container, with the inside of that particular container. Now we're going to have pressure that is building inside, and that's what we are saying is vapor. You are having vapor pressure. Now, vapor pressure, we define it as a pressure, vapor pressure, Vp. We define it as a pressure exerted by vapor. So you just make it like that, Vp to PV. So it's pressure exerted by vapor at equilibrium with its liquid. It's another equilibrium. We have an equilibrium at the melting point. We have another equilibrium at the, when we talk about vapor pressure, to say vapor pressure is the pressure exerted by vapor at equilibrium with its liquid in a closed system. It's important. You see, when we talk about melting point, we didn't talk about closed system. But when we talk about vapor pressure, we say in a closed system. Because if we don't close the system, what will happen? The vapor will definitely escape the container there. Hence, we are saying this one, you must mention that in a closed system. What is vapor pressure? We are saying it's a pressure exerted by vapor at equilibrium with its liquid in a closed system. I hope you got that, because we want you to get these definitions. You will see when you look at question papers, there will always be one or two, one definition in per question there. Now let's go to our third definition now. The third definition is the boiling point. Boiling point, let me write it here. BP, boiling point. The boiling point, we are saying the boiling point, it's not a point, it's a temperature as well, like melting point. It's a temperature at which, remember for water, we're saying it's 100 degrees Celsius, which means that when you say what is the boiling point of water, you say 100 degrees Celsius. 100 degrees Celsius is not a point, it's a temperature. And so I'm emphasizing there that it's a temperature at which the vapor pressure, this vapor pressure that we're talking about here in the container, is now equals to atmospheric pressure. How much is atmospheric pressure? It's 101.3 kilopascal. So we are saying when the vapor pressure, the pressure inside the container, which is called vapor pressure, when it becomes 101.3 kilopascals, then when these two are equal, then we are saying the substance is boiling. So when you say boiling point, we're saying it's a temperature at which the vapor pressure is equals to the atmospheric pressure. We write everything in ways, not in symbols. Vp equals to AP. No, just say vapor pressure is equals to atmospheric pressure. I hope these definitions you will understand and you will always remember them, and they will help you as we deal with this question. Now, our focus in this section, we are going to discuss the relationship in physical properties of alkanes, alkenes, and alkynes. All the 9 homologous series, we are going to look at their physical properties. But you will see, mostly we'll be focusing on alkanes and the other ones, and then alkenes, alkynes, but mostly your questions will be alkanes, haloalkanes, aldehyde, ketones, alcohol, carboxylic acid, and esters. We don't have too many questions that we're asking on physical properties based on alkenes and alkynes. Now we're going to compare the physical properties of different homologous series. So we're going to compare the melting point, the boiling point, the vapor pressure of different homologous series. For a given example from the above functional groups, we're going to explain the relationship between physical properties and the following. Now, these are your independent variable. What the physical properties depend on. The physical property will depend on the strength of intermolecular force. That's number one. They will depend on the type of functional group. They will depend on the chain length. They will depend on the branched chain. So those are 4 things that you will always have in your mind to say, as far as the 3 physical properties, which we call them dependent variables, because this is what we are measuring. So in real sense, question 3 of physical properties are an investigation where we are having dependent variables, independent variables, and control variable. Remember, by now you must know those 3 variables that you have done in your grade 10, that you have done in your grade 11. But we are reminding you to say a dependent variable is that which you are measuring. What do we measure in question 3? We measure the melting point, the vapor pressure, and the boiling point. So those are our 3 dependent variables, because that's what we measure in question 3. So if you are given a question with boiling point, you know that boiling point will be the dependent variable. So the physical properties are the dependent variable. They depend on what? We're saying they depend on the strength of intermolecular force. That is the first thing that we're going to look at. So remember, you have done intermolecular forces in your grade 11, where you talked of your London force, your London dispersion forces, and all those dipole induced, all those type of forces. But now in grade 12, we have even made them much easier for you, because we're going to refer to the London force, we're going to refer to the London force, we're going to refer to the dipole, we're going to refer to hydrogen bonds. So the focus will be on those 3: London force, dipole, and hydrogen bonds. So we won't be saying the induced dipole, induced London, induced dipole, what. We won't be saying those. We'll be calling our intermolecular forces as London forces, dipole, and hydrogen bonds. So this is what we are going to do. But we are saying this melting point, vapor pressure, boiling point depends as to what type of intermolecular force you have. If you have this type, like hydrogen bonds, they are strongest. Obviously, you'll have a higher boiling point, higher melting point, but lower vapor pressure. That's what we're going to talk about. So the main thing that I want you to understand from this page now, as I conclude, is the definitions that I've given you for melting point, that it is a temperature at which the solid phase and the liquid phase are at equilibrium. I said again, the vapor pressure is the pressure exerted by vapor at equilibrium with its liquid in a closed system. Remember, at this equilibrium, we didn't say closed system, but on the vapor pressure one, you must say in a closed system. Boiling point, we said is a temperature. Just like melting point, they are all temperatures. The difference is that boiling point is a temperature at which the vapor pressure is equal to the atmospheric pressure. Remember, learners, you cannot say boiling point is a temperature at which the atmospheric pressure is equal to the vapor pressure. No, it is the vapor pressure that is equal to the atmospheric pressure, because atmospheric pressure, I've indicated already, that is remaining constant. But however, it is the vapor pressure that increases until it reaches the atmospheric pressure. Then the substance will start to boil. Now, in terms of your dependent variables, we said is your melting point, your boiling point, and your vapor pressure and your boiling point. In terms of your independent variable, what do we change? What is that we are going to change throughout this experiment? We are going to change the intermolecular force, we're going to change the functional groups, we're going to change the chain length, and we're going to change the branch. So I've simplified it for you to remember. I've said if chain, Lie branch. If chain, Lie branch, which means that you know the independent variables. When you get structures that you will be given on a question, you are going to check what is changing. It's either what is changing will be intermolecular force, it will be functional group, it will be chain length, or branch. So those are the 4 that the exam guideline talks about, to say these are the 4 things that we're going to change. Remember, to know what is changing, and that change, how is it going to affect, is it going to affect the strength of intermolecular force, and how much energy is going to be needed to overcome that strength of intermolecular force that we are referring to. So you will see when we start with the topics, I've done the definitions, so I won't bore you, I won't go through them again. I'm just reminding you that this melting point, which you said is not a point, it's a temperature at which the solid and the liquid phase of a substance are at equilibrium. And vapor pressure, we said, is the pressure exerted by vapor at equilibrium with its liquid in a closed system. Remember with this one, I said you must say in a closed system. And then boiling point, we said, is the temperature at which the vapor pressure of a liquid is equal to the atmospheric pressure. I hope you got those ones, and you are saying, come exam, I will show them. Now, I've already talked to this slide to say we're having physical properties which now we call them dependent variables. And we said we only do 3 physical properties in grade 12, which is the melting point, the vapor pressure, and the boiling point. Now, when it comes to the independent variables again, we talked about it. I said to you, if chain, Lagrange, so that you don't forget that, okay, in the structures, we'll change the intermolecular force, the functional group, the chain length, and the branch. So when you get structures, you're just going to compare that to say, is the intermolecular force the same? Is the same functional group? Is the same chain length? Is the same branch? And if you have that understanding for this section, you are done. You have the understanding. We are moving. Then you will do very well. Now, in terms of our physical properties, we are saying, remember, we said we do 9 homologous series, which we said is triple A, and C. So there are 3 of them. There are 9 of them. Now, the first 3, which is triple A, these ones, triple A, these ones, we are saying they have London forces. They have London forces, all of them. They have London forces, and London forces are the weakest intermolecular force you will get. They have London forces. Now, when it comes to Hague, I think you like the Hague. When it comes to Hague, we are saying now, these ones, they have dipole forces. Remember, all these structures that we talk about, organic molecules, all of them, they have London forces. So it doesn't matter which one. All of them, they have London forces. So you know that this one, Hague, they have London forces. These alcohols and carboxylic acid, they have what? London forces. The difference is that when it comes to haloalkanes, aldehyde, ketones, and esters, they have dipole as well. So always we will refer to dipole for all these 4 homologous series. However, we know that for them to have dipole, it means they have London force. So you know that already. When you say what type of intermolecular force do you find in aldehydes, you will say dipole forces. But you know definitely that for them to have that dipole, they do have London forces. As London forces, all the organic molecules that we do, they have London forces. So London forces is not a question. All organic molecules have them. These ones, the alcohols and carboxylic acid, we're saying they have now London force, dipole forces, and hydrogen bonds. So they have 3. Hence, they are the strongest. See, they are the strongest. And then when it comes to alcohol and carboxylic acid, we're saying alcohol, they have 1 side of hydrogen bonding, and carboxylic acid, they have 2 sides, which means they form carboxylic acid, they form 2 hydrogen bonds, and alcohol, they form 1 hydrogen bond. So you can see already the meaning of that, to say carboxylic acid will always have the highest strength of intermolecular force because they are forming 2. They have 2 sides of hydrogen bond. They are capable of forming 2 hydrogen bonds. So that a property of carboxylic acid makes the carboxylic acid to have the highest boiling point as compared to the alcohols, though all of them have hydrogen bonds. So when you compare hydrogen bonds and carboxylic acid, you will always go back to the issue of 1 side of hydrogen bond for alcohols and 2 sides of hydrogen bonds for carboxylic acids. So that is very much important. I hope we are moving together in terms of this one. Hydrogen bonds of alcohols and carboxylic acid. I just wanted with this slide to show you so that you are able to see that, okay, because of the only 1 OH now, then that's why we're saying this OH now will be part in terms of forming the oxygen of 1 molecule will bond with the hydrogen of another molecule, and they will form a hydrogen bond. Hence we're saying only 1 hydrogen bond, intermolecular force. Remember, intermolecular force, it means between. Is the between. Inter means between. Molecular force. So is the force between the molecules. Is the force between the molecules. You can see it's between this water molecule, what is this ethanol molecule and this ethanol molecule. So when you look at this ethanol and this molecule, another ethanol there, you can see that there is hydrogen bond. Hence we call it intermolecular force because it's the force that is within. Remember, these ones that are the bonds that we're having here is the ones that we refer to them as covalent bonds, which were sharing of electrons. But the intermolecular force are between. These ones are interatomic forces. These ones are intermolecular forces. And our focus in question 3 will deal with intermolecular forces. Remember interatomic forces, which are the bonds. These bonds, we talk about them in question 4, where we break bonds. Here we break nothing, we just overcome the intermolecular force. It means for us to be able to boil this substance, we must first overcome this intermolecular force between this molecule. And we're saying this intermolecular force is strong because this hydrogen bond is strongest. So because this is strong, it means more energy would be required to overcome that intermolecular force. And when it comes to our friend here with carboxylic acid, we're saying it has 2 sides of hydrogen bond. So this one is capable of forming 2 hydrogen bonds. Hence, we are saying now this will be the strongest as compared to this one. Even if they can all have 1 carbon, but this one now, because it's a carboxylic acid, it will have the highest strength of intermolecular force because it's forming 2 hydrogen bonds. I hope you got the understanding of the 1 side of hydrogen bond and the 2 sides of hydrogen bond, and it will help you as you move, as you deal with this intermolecular force. You will always know. Now let's go to questions, because we want to spend some time doing questions now. The question would be in a graph form. So you'll get a graph like that where you are given a question. What is important is that you know that you have the independent variable, number of carbon. And when I said if chain lip branch, that's what I said to you. So you can see what is increasing as the number of carbon increases, the chain length is increasing. So you can see as the number, or as the chain length increase, what is happening to the boiling point? You can see the boiling point is increasing. The boiling point is increasing. As the number of carbons increase, the boiling point is becoming higher. So you can see there that, okay, as this number of carbons, the boiling point is a dependent variable. It depends on the number of carbons. You see, when we have 4 carbons there, we have a lower boiling point. But when we have 5 carbons, the boiling point is higher. When we have 6, even much higher. 7, 8, even very much higher. So you can see that we have the highest the highest boiling point when we have the longest chain length. As the chain length increases, the boiling point increases. So you are able to see that the equation will be in a graph form. Sometimes it will be boiling point, sometimes it will be vapor pressure, sometimes it will be melting point. So expect any graph, but have the understanding to say this. We are going to change the independent variable, and then we are going to look at the effect the independent variable has on the dependent variable. Remember, we said our dependent variable is the melting point, boiling point, and vapor pressure. Now, we're saying a dependent variable is the variable that changes as a result of the independent variable manipulation. So I always talked about that. And the other thing is that you must be able to generate an investigative question. How do we do that then? You are going to always identify the independent variable and the dependent variable. Hence, you are going to look at what is the relationship, or what is the effect. What is the effect of number of carbon, or of chain length, increasing chain length? What is the effect of increasing chain length on the boiling point of the substance? Boiling point. So the effect of chain length on the boiling point, and then there must be a question mark because we are talking about equation. Or you'll say, what is the relationship between the chain length of a molecule or of a compound, between the chain length and the boiling point? So you can put it like that, but because it's a question, it must have a question mark, and you must be able to get 2 marks. But we are saying in that investigative question, there must be both the dependent variable and the independent. So we're saying, what is the effect of independent variable on dependent variable? So learners, please move with that. I'm telling you, when you get questions, it will help you. Some of these questions will get them in a table form. In a table form as well, you must be able to see which one is the dependent variable, which one is the independent variable. Here they are saying 3 hydrocarbons, A, B, C, were used in an investigation to determine the effect of branching. So already they told you that we're going to determine the effect of branching on vapor pressure. So if you look at this structure, the first one is 1, 2, 3, 4, 5. It's pentane, unbranched. 0 branches here. 0 branch. But if you look at the second one, is 2-methyl butane. It has 1 branch. If you look at the number C there, it is 2,2 dimethyl propane. it is 2 branches. So you can see that as we increase, we're increasing the number of branches. Then we're going to talk about the issue of saying what are the trends? What is trending? What are the trends? What are the trends here? The trends are, as the number of branches increases, the vapor pressure increases. Those are the from this information. It's saying it was 450. We increase the number of branch, it increases. We increase the number of branch again, it increases. So you can see the trend is that, or the trend is that as the number of branches increases, vapor pressure increases. But the question does not end up there. The real question is, what is the effect of increasing the number of branches on the strength of intermolecular force? That is the real question that we must answer. To say, as we increase the branches, the strength of intermolecular force decreases. And as the strength of intermolecular force decreases, the amount of energy required to overcome the intermolecular force will decrease as well, will be less. So as that becomes less, which means that now, because we need less energy, it will have more vapor where we need less energy. You see here, is the strength is decreasing because we have 2 branches. So as you increase the number of branches, you decrease the strength of intermolecular force. Hence, less energy will be required to overcome this less strength of intermolecular force. Hence, we are saying that the vapor pressure will be highest. So vapor pressure, when vapor pressure is highest, always have that in mind. Highest vapor pressure means lowest boiling point. So it means in terms of the structure, boiling point will be the highest in A, and will be lowest in C. Where the vapor pressure is highest, the boiling point is lowest. Where the vapor pressure is lowest, the boiling point is high. So always have that in your mind and it will help you. I hope that helps you now. How do you answer these type of questions that are physical properties? I want us to have a nice conversation here and have an understanding of how to answer questions that involves these physical properties. Number one, the first expectation we have of you is to know the difference in structure. Difference in structure. Is it the chain length? Remember, you are saying what is different. You are saying if chain limb. So that statement I gave you, if chain limb branch, if chain limb branch. So we're saying intermolecular force, functional group, chain length, and branch. These are the differences that you are expecting in the structure. So when I give you a structure, you're going to look at those 4 and say which different do we have out of those 4. That is the first thing you will do. You will look at the difference in structure using the independent variables, which are 4 in this case. I hope we are together on that one. Number 2, you are going to look at the effect on this factor on the intermolecular forces. So we're going here to look at the strength of intermolecular force to say what is the strength of, because we are changing chain length, for example, what is happening to the strength of intermolecular force? Is it increasing or decreasing? That is the S there. Hence I'm putting the S there so that you have that understanding. Now, lastly, we're going to look at the effect on the energy needed or required to overcome the intermolecular force. Always write it like that. Don't call it energy. It's called energy required to overcome the intermolecular force. Now, it's E. Hence I said dice, so that you don't forget. So you look at the difference. You look at the strength of intermolecular force, the effect on the strength of intermolecular force. You look at the energy. Don't forget that dice. It must remind you that I will first look at the difference, then I will look at the strength of intermolecular force, I will look at the energy required to overcome the intermolecular force. Thank you very much. As we move. Now, before we answer this question, many learners who have a problem with question 3 mostly is language issue and the approach, how you are answering the question. Hence, we are always saying to learners when it comes to this question, respond for questions that need explanation. Respond in bullet form, because you are writing different bullets. We'll be able to read those bullets independent from each other because they are bullets. But when it's a paragraph, if the first part is wrong, you are still explaining the wrong part. then it becomes wrong. So it's very much important that you will write this one in bullet form. And then we are saying, when it comes to structure, you will tell us that the type of intermolecular force that we're having. You will tell us about the chain length, whether the chain length is shorter chain length, or is it the branches as well, less branched or more branched, like that. When it comes to melting point, vapor pressure, and boiling point, you either refer to them as lower melting point, higher melting point, or higher vapor pressure, lower boiling point. You can't say bigger. So it's a language issue, because when you say bigger intermolecular, bigger, it has a bigger vapor pressure. We are losing the science there. So hence we are saying this scientific language is important that you use the right language. So when you say melting point, you'll compare it as being lower or higher, vapor pressure lower or higher, boiling point lower or higher. When it comes to the structures, I've talked about it already, to say you are going to look at the intermolecular forces, the functional group, the chain length, and the branch. When it comes to, I talked to this one, when it comes to the strength of intermolecular force, there is no bigger intermolecular force, higher intermolecular force, because bigger doesn't mean stronger. I think you have done magnets. You'll know that a bigger magnet doesn't necessarily mean that it has more strength than a smaller magnet. So it's important that you have the understanding that the strength of intermolecular force is either the other one will be stronger, the other one will be weaker. So when you talk about intermolecular force, there will be stronger and weaker intermolecular force. And when it comes to energy, we'll talk about less energy is required to overcome the intermolecular force. More energy is required to overcome the intermolecular force. I find that very much important. And if we have all these skills, we can now, with no any fear of anything, we can go to the questions. I think you are ready to answer the questions. Now, it's important that if you are given A, B, C, D, if you are given A, B, C, D, refer to them as A, B, C, D to avoid making mistakes. Of maybe you want to write propan 1 all, you write propan 2 all, then the whole meaning is gone. But if you know that I'm answering question on A and B, talk about A and B. And we're going to use the dice now to answer this question. This question was given, you were given compound there, A, B, C, D, which was butane, butan 2O, propan 1 all, and ethanoic acid. So you were given those three, and you were given their vapor pressure. The highest being for butane 204, followed by 24.6 for propan 2O, 2 for propanol, and 1,6 for ethanoic acid. Now, if we check with vapor pressure, we said where there is less strength, there will be more vapor. The vapor pressure is highest when the strength is the lowest. So if we check butane, for example, you can see that butane is the London forces compared to propan 2-ol, which is now having dipole, compared to propanol that is having now hydrogen bond, but one side, compared to ethanoic acid that is having two sides of hydrogen bond. So you can see already when you look there to say in terms of strength, the lowest strength, the weaker intermolecular force is found in butane. Hence, it has the highest vapor pressure. And the strongest intermolecular forces are found in ethanoic acid, as it has the lowest vapor pressure. Because we said if you have the lowest vapor pressure, it means you have the highest boiling point. I hope we're together on that one. So we're saying on the question, they're saying 4 compounds of comparable molecular mass are used to investigate the effect of functional groups on vapor pressure. The results obtained are shown in the table below. Refer to the type. Some of the questions, they will even tell you what you must refer to. They will tell you the independent variable. They will tell you the change that they want you to talk about. So in this one, they're saying refer to the type of intermolecular force. So they're telling you that here you must tell us the different intermolecular forces that they are having. To explain the difference between the vapor pressure of compound A and B. So your focus is on A and B only. And I've already told you that when you write the dice now, you will have first the difference in structure. The difference in structure, which is our DI, the difference in structure. What is different? So they said we must talk about the type of intermolecular force as the difference. What is different? You see, for A, we have London forces. So you know that for A, we have London forces. That is the difference in terms of structure. For B, we have dipole. So you can write dipole forces. That is what we are having for B, dipole forces. And then we have London forces for A. Now, strength, that's the S for strength of intermolecular force. Obviously, London, already I've indicated to you that this one, it has dipole. It means it has London and dipole. So that makes it stronger, obviously, than that one. So you will know that for A will have weaker strength of intermolecular force. Weaker strength of intermolecular force. B will have stronger intermolecular force. Stronger. The strength of intermolecular force of B is stronger than that of B. So you can just say, you can say weaker, or you can just say weaker than, and this one is stronger. So A is weaker than B, and B is stronger than A. Now, when it comes to energy required or energy needed to overcome the intermolecular force, if you are weaker, will need less energy. So the language we're talking about. Now here you are saying less energy will be required to overcome the intermolecular force. Now, when it comes to B, which is having dipole, and stronger, more energy will be required. Look at that question. You're able to ace it and get all your marks by doing that. So it's important, guys, to say always practice. Have many questions before you. Do as many question papers as possible. We have question papers from other provinces. We have previous question papers from DBE. Do as many. Do question 3. Play with it. Play around. Make sure that you answer as many question papers as possible. But you are answering them with what? With understanding. Now, let's look at activity 3. It says, write down the structural formula of the functional group of alcohols. So we want functional group of alcohols. So we won't waste time. We just have to write. Remember, you can't write OH. OH is not the functional group. It's when the OH is bonded to the carbon that it becomes a functional group of alcohols. So it's written like that. I hope we are together on that. You get your 1 mark. But a tertiary alcohol, write the structural formula. Don't forget, always underline here that I'm writing structural formula, because if you don't write structural formula, you will be wrong, because the question said write structural formula. That's why it's important that you must understand the formulas. Now, structural formula of a tertiary alcohol. You see the tertiary alcohol important because now you are able to answer this question. A tertiary alcohol, that is a structural isomer of butan 1-ol. They are not saying draw butan 1-ol. They are saying draw its tertiary alcohol. Remember, butan 1-ol is the OH, the carbon that is bonded to the hydroxyl group, is bonded to one other carbon. So it's a primary alcohol. They are saying now, draw structural formula of its tertiary, because tertiary, it means now it's not secondary, it means it will be butan 2-ol. Butan 2-ol will be secondary. But when you say tertiary, it means now you are having 3 carbons that are bonded to the carbon that is bonded to the OH. So butanol has 4 carbons, so we must have 1, 2, 3, 4. And the OH now is there in carbon number 2. And then you draw like that. I want us to do all the questions, so I'll try to move so that we can finish all the questions. Now, this is structural formula. Is this tertiary? Yes. Why? Because the carbon that is bonded to the hydroxyl group is bonded to 3 other carbons. 100%. I don't want to say the carbon that is bonded to the functional group, because OH is not a functional group. So that is a misconception that you might have. It is a carbon that is bonded to the hydroxyl group that is bonded to 3 other carbons. Remember, for it to be a functional group, this carbon is part of it. So when you define, you are not saying the carbon that is bonded to the functional group. No, because this carbon is part of the functional group. You are saying the carbon that is bonded to the hydroxyl group is bonded to 3 other carbons. Then that makes it a tertiary alcohol. And make sure that your carbons are surrounded by 4 bonds all the time. Because if you forget 1 carbon with only 1 bond, the whole structure is wrong. Let's move. Learners investigate factors that influence the boiling point of alkanes and alcohols. So they told you that now we're talking about alkanes and alcohols. Remember, alkanes, they have London forces. Alcohols, they have one side of hydrogen bond. In one of the investigations, they determined the boiling point of the first three alkanes. So this statement has nothing to do with alcohol. They're talking about first three alkanes. What are they? First three alkanes is your methane, is your ethane, and your propane. You know them. You know them. You know them. You must be seeing them by now. Now they are saying, write down an investigative question for this investigation. Remember, I just told you that investigative question is very much important. I'm trying to be fast. Now, first thing that you will do, you will say, what are my variables? What am I changing from methane to ethane to propane? You see, this is the same functional group. So the intermolecular force is remaining the same. It's London forces in all of them. But this London force is increasing. How is it increasing? We're increasing the chain length. Remember, this is CH4. This is CH3, CH3. This is CH3, CH2, CH3. So you can see the chain length is increasing. Oh, yes. So that is our independent variable. What is the effect of chain length on what? On the, they are measuring what? Boiling points, on the boiling point. Or you'll say, what is the relationship between the chain length of alkanes and of the first three alkanes and what? And boiling point. Your question must end up with a question mark. And then you got your 2 marks there. Fully explain why the boiling point increases from methane to ethane. 3 marks. You are dicing it again here. So you are saying, what is the difference? The difference is the chain length. You are saying the chain length increases. Chain length, it increases from methane to ethane. Chain length increases from methane to ethane to propane. So from ethane to propane, the chain length is increasing. And as the chain length increases, the strength of intermolecular force is increasing. As the strength of intermolecular force is increasing, more energy will be required to overcome the intermolecular force. You see, it becomes easier now for you to answer that question. Now, let's look at 3.4. 3.4 is saying they find that the boiling point of propan-1-ol, they're bringing the alcohol again, is higher than that of propane. Explain. You see, when they say type of intermolecular force, they are saying we're giving you different functional groups, we're giving you different homologous series. So you're able to see that. So, okay, explain this observation by referring to the type of intermolecular force present in each of these compounds. 3 marks. You are dicing it again. You are saying what is different. Propan-1-ol has hydrogen bond. Remember, you can talk to the one side when you are comparing it to carboxylic acid. But when you're comparing an alcohol and other homologous series, you'll just say it has hydrogen bond. But when you compare it to carboxylic acid, you must qualify it to say alcohol have one side of hydrogen bond, carboxylic acid has two sides of hydrogen bond. But when it comes to this one, because you're comparing with another homologous series, you can simply say this one has hydrogen bond, propane has London forces. You go to the strength. You say the strength of intermolecular force for propan-1-ol is stronger than propane. For the strength of intermolecular force for London forces is weaker than propan-1-ol. So you can talk about the propan-1-ol or you can talk about propane, whichever you choose to talk about. If you are talking about propan-1-ol, you'll say, okay, in terms of the intermolecular force, you will tell us about the intermolecular force of all the 2 homologous series that we are having, which is propan-1-ol and propane. So propan-1-ol has hydrogen bond. Propane has London force. When it goes to the strength of intermolecular force now, you're going to say propan-1-ol has stronger intermolecular force than propane. More energy is required to overcome the intermolecular forces in propan-1-ol than in propane. You are comparing. So you can just simply dice it, and then you got your 12 marks, and you are a happy person. Now let's move to question 4, activity 4. Learners use compounds A to C shown in the table below to investigate a factor which influences the boiling point of organic compounds. Already you can see the first thing that you are looking at is saying, what are we changing? Already you know the dependent variable here is boiling point. But now what is changing? You check 1, 2, 3, 4. 1, 2, 3, 4, 5, 1 up to 6. So you're able to say, what is changing is the chain length. Chain length is changing. That is the difference between A and B. You see difference between A and B, CH2, difference between B and C, CH2. So you can see that these belong to the same homologous series. Remember, the definition of homologous series says they are described. These organic molecules are described by the same general formula, or each member differs from next by CH2. So you can see this one differs from next by CH2, and this one differs from next by CH2. So you're able to see that we're increasing the chain length. Now, without wasting time, let's move. It says, which one of the compounds A, B, or C has the highest boiling point? I know. You'll know that you're going to say is C. Why? Because C has the longest chain length. As the chain length of C is longer than the rest. It has the longest chain length. Now, for this investigation, write down the independent and the dependent. You see this question of independent and dependent. We're not just talking about. It's a question that will get it in the exam. Already you know the dependent, we're measuring boiling point. Dependent is what we're measuring, is boiling point, and what is changing is chain length. Remember we said our independent variable is if chain, leaf branch. In this case, they are changing the chain length. That becomes our independent variable for this particular question. Write down the name of the type of van der Waals forces that occurs between the molecules of compound B. You see, it's important that you know that these forces, they are referred to as van der Waals forces, including your London force, your dipole. So that when they say van der Waals forces, now you don't have problems of saying, hey, what will be these van der Waals forces that I'm talking about? So your London forces, your dipole, they are van der Waals forces. But in this case, because we're talking about alkanes here, we're talking about London forces. So you know, write down the name of the type of van der Waals forces, the force that we're having here. This question is so simple. This question is saying what type of force do we find in these compounds that we are given on the table? And that is London forces. But now the learner would be confused by van der Waals forces. But now that we are doing them before exam, you know that these are van der Waals forces. Even if it was dipole, you will still say dipole. But in this case, it is London forces. Hence, we are referring to this as London forces. How will the vapor pressure of 2-methyl pentane, 6 carbons, 1 on the branch and 5 on the parent chain, compared to the compound C? C is 1, 2, 3, 4, 5. So they all have same number of carbons. So they all have C6H, it must say 14 because they are alkanes. They all have that. So it's what we call now chain isomers. Yes, these are chain isomers. So now you are able to see that 2-methyl pentane and hexane. Immediately when we have a branch, the strength of intermolecular force decreases. And when the strength of intermolecular force, you will say, this is important, you will say the vapor pressure, this is how you answer the question. The vapor pressure of 2-methyl pentane is lower than that of C, which is hexane. So it's lower than, because this one has less strength of intermolecular force because it has a branch. Hope we got that. Let's look at finishing that activity. The learners now compare the boiling points of compound D and E shown in the table below. You can see now we're having an alcohol and a carboxylic acid. You know we're having hydrogen bond here. You must write hydrogen bond in full. All of them, they have hydrogen bond, but this one has one side of hydrogen bond. This one has two sides of hydrogen bonds. So obviously, E is stronger than the other one. So what is the question saying? How does the boiling point of D compare to that of compound E? So obviously, you are saying E has a higher boiling point, higher than, you write the one of, how does the boiling point? You must be very careful on what comes first on the question, on the statement. How does the boiling point of compound D compare to that of compound E? So you are saying you start with D as they are written there. You see, if you just rush, you are talking about E, but you'll say higher, E is higher than D, but the question started with D. So even when you respond, you will start with D. So you'll say compound D is higher. The boiling point of compound D, the boiling point of compound D, which is this one, which is an alcohol with one side, is lower D. Alcohol is lower than carboxylic acid. That question looks like a very simple question, but it can be confusing at times. So it's important that you write D first, Then you write E here before you choose your option there. It is okay. The boiling point of D is lower than E because this one is a carboxylic acid. I think you got it. And fully explain. So you're going to explain, you're going to say this one has one side of hydrogen bond, this one has two sides of hydrogen bonds. You're going to indicate that more energy will be required to overcome forces in of E than in D. More energy will be required for E than in D because the strength is higher or stronger in E than in D. So you are able to respond that. I wanted us to look at the graph as well. Already we shown, you can see that as the number of carbons increases, the boiling point is increasing as well. So they are saying the relationship between the boiling point and the number of carbon atoms in a straight chain molecules of alkanes, carboxylic acid and alcohol is investigated by in caps P, Q, and R. We are given three caps. Define the term boiling point. Remember we said it's not a point, it's a what? It's a temperature at which the vapor pressure is equal to the atmospheric pressure. Now for cap P, write down a conclusion that can be drawn from the above results. For curve P, you can see for curve P there that as the chain length increases, the boiling point increases. Or you can just talk about number of carbons. As the number of carbons increases, the boiling point increases. So they increase together. And then identify the curve P, Q, or R that represents alkanes. Remember, they said we have alkanes, we have alcohols and carboxylic acid. And look at the order that they are given there. They say alkanes, they say carboxylic acid, they say alcohol because they want to confuse you. But your job is to arrange them to say it will be alkane first, followed by alcohol, followed by carboxylic acid in terms of strength. Remember, these ones we said alkanes P will be alkanes because they have the weakest intermolecular force, so they will have a lower boiling point. And then followed by alcohol, which is Q, followed by R, which is now carboxylic acid with the highest boiling point. So you are able to get it from there. So for 5.31 alkanes, we said is P. For carboxylic acids, we said carboxylic acid is the highest, so it's R. So you are able to answer that question. And then they said, explain the answer to question 5.3 by referring to the type of intermolecular force present in alkanes, carboxylic acid, and alcohol. The relative strength of this intermolecular force is NH, which is the same thing that we have been saying. So you're obviously going to say alkanes, they have London forces, alcohol, they have one side of hydrogen bond, carboxylic acid, they have two sides of hydrogen bond, and then more energy will be required the strength of intermolecular force in carboxylic acid is stronger than in alcohols and alkanes, and we are saying more energy will be required to overcome intermolecular forces in carboxylic acid than in alcohol and alkane. So that's how you will get your 11 marks. So you can see that this is a section where you must be able to get your answers. Now let's look at activity 6 as we conclude. Now we are saying there, define the term structural isomer. Then you are going to say these are organic molecules that have the same molecular formula but different structures. Remember structural formula. Remember the difference is always on the structure that is given. What type of isomers, positional, chain, or functional are these? The ones on the statement there. What types of isomers? You can see you have 2,2 dimethyl propane, 2-methyl butane, and pentane. So you can see that these are chain isomers. They belong to the same homologous series. So these are our chain isomers. They have branches. You can see those are chain isomers. Explain the trend in the boiling point from compound A to compound C. So you can see that 3 marks. You can't just say as we move from A to C, the boiling point increases and you expect to get 3 marks. That would be 1 mark. Indeed, it increases from A to C. You see it's 9, it's 28, it's 36. But you must be able to tell us what is changing there, what is different there. And then you are able to say, as we move from compound A, we are decreasing the number of branches. You can see we had 2 branches in A, we have 1 branch in B, we don't have 0 branch in A. So C is unbranched, it will have a highest boiling point. So strength of intermolecular force increases from A to C. So that is the trend. So your trend will talk to the boiling point, it will talk to the strength of intermolecular force, it will talk to the energy that is required to say, oh, more energy is required in C, hence we are having the highest boiling point. Which one of the three compounds, 7.4, which one of the three compounds has the highest vapor pressure? Highest vapor pressure means lowest boiling point. So you're able to say it is number A. A has the lowest boiling point, which means it has the highest vapor pressure. So these activities must help you draw structural formula of compound A. All you have to do, you know that you have three carbons, so it will be easier when you have three carbons. You're just putting the methyls there, 2,2. So you put your methyls there fast without wasting time. You are able to put your methyls, 2,2 dimethyl, and then you get your propane there, and ensure that each carbon is saving 4 bonds around it. And then look at the number of marks there. It was 3 marks. You will have got so many marks that you'll be having. You'll be having those marks. Now let's consolidate now as we finish this section. A scientist investigates a factor that influences the boiling point of alkanes. He determines the boiling point of the first 6 straight chain alkanes. So that is from methane to ethane, first 6. Methane to hexane. Number 6 is hexane. Which one of the following is the independent variable? So if you move from methane to ethane to propane to butane to pentane to hexane, obviously you're increasing the chain length. So that becomes your independent variable. This is what we are changing, because what we are measuring is the boiling point, which is our dependent variable. Now the last consolidation activity, it says which one of the following combinations correctly indicates the strongest intermolecular force found in ethanoic acid and methyl propanoate respectively. This was an English question paper, because now if we don't know what respectively mean, they are saying in that order, which means the first one must be ethanoic acid, the second one ethanoic acid. You cannot start with methyl propanoate and then ethanoic acid. So let's check. Ethanoic acid, we agree it has hydrogen bonds. Esters, they don't have hydrogen bonds. Then ethanoic acid, it does have dipole, but they're talking about the strongest. So it's wrong. It's not strongest. It's hydrogen bond, the strongest. So hydrogen bond. Correct on that one. Let's go this side now. In terms of methyl propanoate, it has London forces, but it's not the strongest. It has London forces, not the strongest, but it has dipole forces, which is the strongest intermolecular force in them. Remember what we said: triple A, and C. So you're able to know that all these, they have London force, all these they have dipole. In this case, the ester here, it has dipole, and all these they have hydrogen bond with alcohol, one side of hydrogen bond, and carboxylic acid, 2 sides of hydrogen bond. So you're able to see that the correct answer will be number D. And with that, I would like to thank you and leave you with this quote from Albert Einstein, who said, anyone who has never made a mistake has never tried anything new. We are saying keep on trying, keep on doing as many problems as possible, and you will make it till we meet again. Thank you very much.